In the last lecture, we start considering lossy source coding with site information. First, we considered distribute source coding and want to introduce rate distortion in this. So we want to consider lossy distributed source coding. But it turns out that this problem is still unsolved. Therefore, we look at a more special case, so that this lossy source coding with site information. We look at this model here. So we have a source, like in distributed source coding, it produces two sequences, xn and yn. Yn is sent directly to the decoder, and xn is encoded, so we want to have some data compression to an index w, and the decoder receives yn and the index w. And he wants to estimate xn by x hat of n in such a way that the expected distortion is smaller or equal than d. So this is really a special case of distributed source coding with rate distortion. When we look at the proof of Weiner and Zith, it turns out that the coding and analysis is a little bit trickier than for the previous model of Slepian-Wolf. So what we learned, the trick we learned new was the random variable u. So we have to introduce a new random variable u and call this random variable an auxiliary random variable. So we introduce a channel from x to u, where the alphabet of u is this u here. So u represents a code word sent from the encoder to the decoder. And we further define a function f that maps symbol in u times y to x hat. So the reconstruction x hat of n has x hat I is equal to f of ui and yi for all I. And we write the corresponding sequences mapping x hat of n as fn, un, and yn. So in principle, it's the same like we do in Slepian-Wolf, but the thing what is different is that we don't use directly the alphabet x, we use the alphabet u here. Somehow we decouple the output of the source from the coding. So, and we have, of course, you can have the feelings that we use a bigger alphabet and we have more possibilities. So we use a code book which uses letters from u. So we can produce, we can calculate the random variable u by using this channel here, which is this auxiliary channel here. And then we use this random variable u to produce our code book. So let's look at this in more detail. So we generate 8 as before 2 to the n r plus r prime code words un of w and v. You see, we use here again also the binning idea. So we create more than one code word per index here. So r prime is 2 to the n r prime code words we have for one index. And in totally we have 2 to the nr in indices. So w goes from 1 to 2 to the nr, and v goes from 1 to 2 to the nr prime. So in totally we choose n times 2 to the n r plus r prime symbols by using the random variable pu, which we have calculated from pxu. And you can observe we use the same binning idea as we used for Slepian-Wolf. And now the idea is that if the source produces an xn, we try to find a pair, or the encoder try to find a pair w and v such that xn and un of w and v is jointly typical concerning x and u. If he finds such an index w, he sends this index. Otherwise, he sends w equal 1. Of course, if you find more than one index, then you need a function which he chooses. We always can assume that he takes the first one in the list if we order it. Now the decoder, of course, has the same code book like the encoder, and he looks, he received W and he received Y to the N, and now he try to find a V tilde such that Yn and Un of W and V tilde is jointly typical concerning Y and U. If there is one or more such V tilde, choose one as V tilde and put out the reconstruction X hat of N. We can assume that this function always takes the first one and we order the code book. And if there is no such V tilde, then we put out some dummy word here. That's the idea of the code construct. So the new idea is really that we somehow decouple the code book from the output of the source. And we make, of course, this alphabet we make bigger. We have a bigger alphabet and more possibilities. And therefore, it's easier to prove it. You will see it in the proof, or you saw it already in the proof. So the idea is really this use. That's a new idea we use here. And binning, of course, was the old idea we already used in the previous model, and also random coding. These are the three main tricks we use here. And I already showed you that that we can achieve this region here, the minimum over all these auxiliary channels and all functions such that the expected value of x and fu and of f and u and y is smaller equal d of the mutual information of x and u minus the mutual information and y on u. Today we will do the converse, and for the converse we will start as usual, like that there are 2 to the nr indices w, such we can start that nr is greater equal h of w. And again we use it, this function rwz, where we showed that this is a achievable part somehow, is a convex function.